Okay, so I'm giving a summary about the VST photometric H-alpha survey of the galactic plane and bulge. And I'm talking on behalf of the whole consortium, and in particular, I listed here Janet Drew, who is the PI of the project, Robert Grimmel, who's leading the new data release that we are planning, and also Maria Monguiot, that did a lot of work on the twin survey in the Northern Hemisphere. Today we have seen the origin of the name for the Ultra Vista survey. And I have to say, I'm not sure I remember why there is a plus, because I was doing my PhD at the time and I was concerned with other things. But I think the plus may refer to this bulge coverage, because it wasn't originally planned. So in the talk, I will give an outline of the summary, describing also the data releases, it was coming in the future, and also giving some summary of the science that has been done so far with VPHAS+. But also, I really like to show this figure that comes from a recent ESO picture of the week, where you can see all the details. And I suggest you to go actually to the online figure where you can zoom in and you can see the interaction of these very bright newborn stars with the emission nebula surrounding them, the dust lanes in this part of the figure, also the reflection nebula here. So this is the footprint of the survey. You can see the survey didn't manage to cover some parts of the plane due to the time limitations, but the important thing was that managed to cover all the bulge area that is also covered by the survey VVV in the infrared, and also this part of the mid-plane. So there is a complete coverage of the mid-plane, the real center part of the galactic plane. The survey, like many other surveys done at the VST with the Omega Cam, was done in 4 photometric bands in this case. In particular, there was the addition of a narrow band filter centered on the H-alpha line. The importance of this filter is because for the idea of selecting young stars, emission-line stars, also interacting binaries. So due to the requirements of going down to at least 20 magnitudes, the exposure times were selected in this way. In particular, most of the time was spent on the U band, which is the most time consuming, and also the H-alpha band because of the narrow filter. The G band was going slightly deeper than the others because it's used for producing this the master catalog list. And you can see that there were at least of the order of 35,000 images being acquired. The survey was also projected in a way that the attempt was to leave less gaps possible between the CCD. So each pointing was made of 2 shifted images trying to cover the gaps between each CCD. And you can notice these are not really in scale. The real scale is more visible in this image here. But for the H-alpha filter, we used 3 offset positions, and the reason why we use this particular different offsetting is because the H-alpha filters that was projected by the VPHAS+ consortium has this crossbar in between. So a very large part of the sky was covered by the shadow of this bar. And of course, this filter also is made of 4 different parts that needed to be really well tuned in order to have a very similar central wavelengths. And later on, also, there were 3 offsets for the G band in order to ensure a larger coverage and a better depth for the survey. Here, there are some other numbers about the survey. In particular, it's very interesting to see that the median seeing was very good, in particular for the R and I bands, and the G and H alpha bands still had median seeing below 1 arcsecond. The U band was typically observed in less good conditions. But overall, in a previous slide was written, the survey was split in two different branches. The red filters were observed together, and the blue filters were observed together. But the R band was observed both with the red and the blue filters in order to join them together. So having repeated observations in the R band in order to create a sort of uniform catalog and a spectral energy distributions. And you can see here also the magnitude depths. They are slightly deeper for the G band, which is making the catalog for detection of sources in the survey. So there were so far 4 data releases. The first one is not listed here in this slide. Contained essentially the source catalogs and the photometry for each individual band, and it's available in the ESO archive. The first one having the combined, the merged photometry and source list was also available in the DR2 here and available from the CDS web pages. Later on, there was a DR3 that was also hosted by the Omega Cam archive from WFAU. And then the 4th data release was the last one, containing all the data coming from VPHAS+. And now we are projecting this new one, which is the homogeneous calibration of the whole survey. And Robert Greimel is leading the project, and there will be a paper, hopefully in 6 months, describing it. So first of all, the attempt is to improve the astrometry, because the astrometry coming out from the pipeline was registered on the TUMAS frames. And you can see here in this in this panel, applying the epochs from Gaia already improves a bit the RMS of this astrometric solution. But if the astrometric solution is directly done by using the Gaia reference frame, there is a very significant improvement that here in this larger panel is highlighted for the different bands G, R, and I. And you can see that this RMS in milliarc seconds is much smaller compared to the original one. So this is one important feature of the next data release. That can be still improved because there is a dependence also on the azimuth distance of the pointings that I think the plan is trying to apply this one, and you can see that essentially this additional error that is introduced into the astrometry is mostly concentrated in fields that have this color and correspond to larger zenith distances when the telescope is pointing at the sky. Then there was already this correction applied in the previous releases, that is the illumination correction. Essentially, you need to correct the images due to effects happening into the CCDs and as radial and perpendicular relations that are corrected by the pipeline done by CASU. And in addition to that, there is a problem that has to be considered, that each filter, being very large, has a dependence on the position where the sources are detected. So the response of the filter changes a bit with position. And so here was a test done in the lab, I think at the Munich Observatory, sampling the response in this orthogonal positions. For the H-alpha filter was done in the individual quadrants of the filter itself. So here you can see a comparison of the Gaia photometry with respect to the G, R, and I. So these are the corrections transforming one system into the other. And they are important because now the photometry in the data release 5 of VPHAS Plus is going to be calibrated against Gaia DR3. And so, of course, there are some things to be taken into account, that because the filters of Gaia are very large, but overall the photometry is behaving very well. And you can see that it's behaving, the new calibration is going so well that it's also possible to map again these variations of the filters as a function of position on the CCD. And so you can see here these differences for the G band, the R band, and the I band expressed as color-coded. And these numbers represent the 10 millimax, for instance, 20 millimax. And you can see that they have a radial dependence. But overall, the scatter between the effect introduced by the filters is overall of the order of 10 millimax. It's much better going for instance, for the red filter respect to the G band, which has a larger variation in the corners. And this is consistent with the previous results that were only sampling this kind of behavior in this just straight lines going from a corner to the other and perpendicular to the array. So the U band is one of the most difficult to calibrate, because while the G, R, and I bands are covered by the Gaia filters, the U band is just at the edge of it. In addition to that, the U band also has a problem with the atmosphere of the Earth, so it's depending on the weather conditions. But the calibration is working successfully, and is also being done by using this method described by Glaserbrock, which identifies anchor fields throughout the survey and work out the calibration among these fields. So very good observations are selected as anchors, and then there is a polynomial interpolation among all the fields of the survey. A similar thing is done with the H-alpha band, but the H-alpha band also is calibrated by using, it needs to have a fixed offset with respect to the R band. And this fixed offset is determined by essentially knowing the properties of stars. We know that the H-alpha has a strong absorption in the A spectral types, and so where the strongest absorption is known, the fixed offset is determined. And here you can see, unfortunately, the grayscale is difficult to see on the screen, but these are calibrated fields. So you have the U minus G and G minus R color diagram. Here, the G minus R, R minus I, and this is the R minus H alpha, R minus I. And this offset refers to the new calibration. So in each image, there is an offset that needs to be applied. And so here we are combining a very large area, so 80 square degrees, which is basically 80 pointings of VPHAS Plus. And you can see these two red lines are the red line for the A2 stars, and these are the for the G stars, I think G0, while the blue lines are essentially the main sequence, the colors for main sequence stars. And there is this circle here that represents a particular A0 star with a given reddening. So you will have the most of these fields from VPHAS Plus are very reddened. And it's very difficult to see it here, but the end doors have here a branch, implying that essentially even the nearest end doors have typically a reddening of a few 0 point something magnitudes. And in particular is the very last fix to the overall calibration that is done by selecting classified stars from the Gaia DR3 selection and cross-match with Tumas and Wise that was done by Zhang, Green, and Rix recently, where essentially they determine the spectral types of these stars by training a machine learning algorithm that used as a training sample well-characterized Lamo stars that have spectra. And so this is the very last fix, and you can see a very good overlap of the main sequence and the reddening lines, signifying that the VPHAS Plus survey is going to achieve this overall calibration throughout the whole galactic plane. Now let's go more into this direction of science that we can do with VPHAS Plus. In particular, we can see three color diagrams showing the same colors, the R minus H alpha versus R minus I. For the VPHAS Plus survey, the I gaps, which is this combination of the IFAS survey and UVEX surveys in the northern hemisphere, and the photographic plate photometry coming from this supercosmos H alpha survey. So the three color diagrams are showing the same part of sky, and VPHAS Plus is detecting 2 times the number of sources detected by IFAS, and you can see how the two CCD surveys are doing much better compared to the photographic plates. And so the difference between IFAS and VPHAS Plus is mostly likely due to the magnitude depth that is slightly deeper for VPHAS Plus, also the higher, the better sync that allows you to disentangle more sources, of course. And so VPHAS Plus is going to contribute, or actually contributing to the target selection also for WIV, in particular for the this sub-survey that is also led by Janet, where we are trying to observe all the young stars and interacting binaries in the galactic plane. And the reason is because, of course, there is a part of the galactic plane that is visible in the north and is covered by the two surveys. And so also this is a way of checking how the calibration is working for the survey overall, and also seeing possible variability among sources, right? So now here we are starting going more into detail of the science, and in particular, well, there was the survey paper that has been cited by 200 other works, and it's very interesting that it's a very large variety of science that is covered by these papers, because we start from massive young stars, going to the low mass ones, open clusters, a very large range of emission-like stars, and going at the end of stellar lives with planetary nebulae and white dwarfs. So let's start with massive young stars. And the southern galactic plane is very rich of these massive star formation sites. In particular, one of the most active ones is this the Carina arm of the Milky Way, where you can find the Western Loon 2 and this other cluster that I don't remember the number, I cannot really, NGC 3199. Here in this figure, you can see the galactic equator. And this is a 2 square degree image. So it's combining 2 pointings. Well, it covers 2 pointings of VPHAS plus, but they may be oriented in a different way, so it's more than 2 pointings. So there were 2 papers on this region. In particular, Mike Moore-Smith worked on the selection and characterization of these OB stars. So at the time, the calibration was not uniform, so we had to calibrate the photometry using the known properties of stars. So identifying what is the red and main sequence, and then selecting what are these blue stars. And so essentially the selection was working fine because down to this B spectral type, you can avoid the majority of stars, G stars, F stars here, they are reddened. So all these objects were candidate OB stars in the Carina arm, which is located between, I think, 2 and 7 kiloparsecs away, at least looking in this direction of the sky. And so there was a selection of a very large number of OB candidates, going much deeper compared to previous work. A very significant number was made of O-type candidates, and in particular, combining also with the other photometry for VPHAS plus, was possible to identify whether there were some emission line candidates among them, and other kind of objects, for instance, subdwarfs, because if you assume a given distance and they are located along the sideline, there could be different classes of objects. So there was a spectroscopic follow-up that confirmed the majority of them to be OB stars. And of course, there was some contamination from the objects being here, so A, F, and G stars. And so this was a significant number of new objects found in this, and showing how effective can be a survey like this one at identifying new young stars. Later on, Janet led some other papers looking again at these regions in the Carina arm, but combining VPHAS plus with proper motions. So the focus of these papers was the study of the dynamical interaction within the open clusters. And in particular, they identified a few candidates of ejected O-type stars. And by tracing back the movements of these objects to the possible sites of ejection, they confirmed that this flight time was shorter than the age of the cluster, so the association was very likely. And essentially, they showed that within these clusters, there were mechanisms ejecting stars in the last 1 to 2 million years. And so in other papers later on, also Janet and her friends analyzed a much wider region. Here I wrote 24 square degrees, but I realized that I cannot do maths, and actually it was a much larger region, 48 square degrees. So they identified 4,000 OB candidates with the same methods. So a huge number of O and B stars, and among them, by looking at the proper motions, about 10% seem to be ejected from these clusters that are in this wide region. And of course, the number depends on where you put the limits of what is a runaway star, what is a walkaway star. And by taking spectra, in particular, they looked at infrared spectra because the stars are very red, and so it was easier to take infrared spectra. They confirmed 30% of these objects to be runaway stars. So confirming the selection by using only the two-dimensional motion. In particular, they also noticed a kind of periodic behavior of the proper motions that essentially is saying is related to the original velocities of the molecular clouds that may be still maintained by these OB stars when they are formed. So they follow the original motion of the clouds. And in particular, it was also possible to find likely moving groups within this very large area. So, okay, here there is something about the young stars. There should be talks after me, so I'm not going to say too much. I only like to highlight how beautiful this is. This image is. I think this was from the press release of VPHAS Plus. And so with this, with VPHAS Plus, it's important that you have H alpha and U band photometry so you can estimate accretion rates for the young stars and compare the two methods coming from the UV-XS and the H alpha XS. But you will learn about this later. Now, something that is now changing a topic, we are going to look at older stars. So in these papers, they analyzed the authors analyzed the selection of old stars, in particular these symbiotic stars that are binaries where a giant star is transferring mass onto a white dwarf. They could be supernova progenitors. And the authors essentially selected the stars by looking at the H alpha emission from VPHAS Plus and combining that with infrared photometry. They developed an algorithm for characterizing the candidate symbiotic stars and doing spectroscopic follow-up, confirming a large number of them. And then finally, there is something about planetary nebulae. The high resolution of VPHAS Plus has been very useful for identifying some candidate central stars in the planetary nebulae and also characterizing them. In particular, this one, there seem to be two stars, but essentially only one is the central star. The other one is not linked to the other one dynamically. So they happen to be in the center, but only one, I think the hot one, is the central star of the planetary nebula. And finally, I like to self-promote a paper that I published when VPHAS Plus started producing data, where we selected new candidate white dwarfs in the galactic plane belonging possibly belonging to open clusters. So you can imagine these very faint stars around 19th magnitude, 20th magnitude, and trying to identify those that are members of open clusters. We follow them up with VLT Force 2 in order to obtain spectrophotometric parallaxes. Even with Gaia, parallaxes of these faint objects in the galactic plane are very difficult to constrain their membership to the open clusters. But essentially, the selection worked again using the U color, identifying the known ones, which are these blue symbols, and the candidate ones that are the red one, and then determine their physical properties, membership to the clusters, whether the distances are matching the distance of known clusters, and then so determine the possible mass of their progenitors. In particular, the work was very interesting because we found the candidate maybe is coming from a progenitor that had a 9 solar mass, was a 9 solar mass star. So a very massive star that didn't become a neutron star, managed to become a white dwarf. And this is very interesting because this boundary between the formation of neutron stars and brown dwarf is still not very well defined. But of course, we will need maybe higher resolution in order to know whether this is a binary system that messed up everything. And we don't know if it was a merger, could have been a merger in the past. So to summarize everything, VPHAS Plus ran between 2011 and 2018, covered about 2,000 square degrees, and went down to a magnitude of 22.5 for the G band. You can see also from this image, the scene was most of the time, on average, below 1 arc second. And you can distinguish the individual sources within these very crowded regions of the sky. And it contains 900 million unique sources, which is a very large number. So in future, we already have this calibration complete. There is also only some fine tuning to do. It will be published next year, hopefully in 6 months. New astrometry, new band merge catalog. And VPHAS Plus is able to do all the science that I've shown and even more, hopefully. And thank you for listening.